Thank you very much. Welcome. Very good. Very good. Welcome to Perimeter Institute here in Waterloo, Ontario, Canada, and welcome to this Perimeter's public lecture series from the Mike Lazaridis Theatre of Ideas. My name is Greg Dick. I'm the Director of Educational Outreach here at Perimeter, and it is a pleasure to welcome everyone here, those of you here in the theater and those of you watching online. Now, tonight's lecture will last approximately 1 hour and will be followed by a question and answer session. For those of you watching online, we have Dr. Damien Pope and a team of PI researchers behind their keyboards ready to engage in conversation and answer questions throughout the lecture. If you want to participate on the Facebook feed or on Twitter, use hashtag PI Live. And also, if you have a question for our presenter, use hashtag PI Live and get that question in early so that it can make it all the way to my phone and I can ask. And now it's my pleasure to introduce tonight's very special guest speaker, Dr. Chad Hanna. Dr. Hanna is currently an associate professor at Pennsylvania State University, but he has close ties to Perimeter because he was a senior postdoctoral fellow here from 2010 to 2013. Dr. Hanna was awarded the National Science Foundation Career Award in 2015 and the Freed Early Career Professorship at Pennsylvania State University in 2016. Dr. Hanna and his research group are trying to enable multi-messenger astronomy through gravitational wave observations of neutron stars and black holes at LIGO. He was the co-chair of one of LIGO's largest astrophysics working groups, the Compact Binary Coalescence Group, and he was recognized as a contributing author when the LIGO project won the Special Breakthrough Prize in Physics in 2016. And tonight, Dr. Hanna will discuss how these new windows onto the universe have changed our view of the cosmos and what new wonders that may be unveiled in the decades to come. Ladies and gentlemen, please welcome Dr. Chad Hanna.
Hi, everybody. It is a pleasure to be back here at Perimeter Institute. It is a great honor to be in front of you this evening giving this public lecture. I'm going to start tonight with something I've never tried before. So I have in my pocket something I should probably not have in the theater. It's my cell phone. I'm supposed to turn it off, I think. I want to ask a poll, so we're going to raise our hand. As you just heard, I'm part of a collaboration that right now has, just as of Monday, embarked on the most sensitive measurements of gravitational waves in our universe ever. We expect to detect a new binary black hole about once every 5 days. This whole system, thanks to the work of thousands of people, is now fully automated, running online, and when this happens, I should get the alert on my phone. So, this lecture is about an hour, give or take. If I keep talking like this, it'll last a lot longer. About an hour, so I figure we got a 1% chance of a new discovery coming during this lecture. Now, the good news is I'm terribly unpopular, so no one's going to call me otherwise. But the bad news is spammers, they call with the phone, and so we probably get like a 2% chance of getting a spam phone call. So what I want to know is, how do you like those odds? Should I at least leave it on vibrate so that we could all take part of that discovery? All right. Okay, well, you never know. For as long as people have been leaving clues about previous civilizations, it seems that we keep finding evidence that they've been interested in the night sky. In the late 70s, from aerial photographs, it looked like in this field in Scotland that there was this peculiar series of pits arranged in roughly an arc. Archaeologists excavated this site, and sure enough, it appears that there are a bunch of holes that looked intentionally dug by people at some point. These holes were dated to approximately 8,000 BC, so 10,000 years ago. And this is interesting because a hypothesis for what this is that these pits were somehow tracking the phase of the moon, the position of the moon in the sky, as a way of tracking time. And if this is true, this means that this is perhaps one of the earliest lunar calendars that could be used to track the coming seasons. People were interested not only in the practical sides of astronomy, which is absolutely the oldest scientific discipline by far, but also perhaps maybe something a little more mystical, even divine. We're not sure necessarily what this is. The Niebuhr Sky Disk from the Bronze Age, but it seems to be one of the earliest depictions of the cosmos, perhaps showing, for example, the full sun and the day, or maybe the full moon, crescent moon, and what people think might even be an image of the Pleiades star cluster. People looked beyond just the sort of static or cyclical aspect of the sky, and were already noticing various transient phenomena. Certainly comets and things like that, but even some things that are much, much, much more profound that we now know of as supernova. Chinese astronomers referred to these over the last 2,000 years roughly as guest stars. This is the product of when certain stars grow old and die and explode, and for a brief moment in time, if they're close enough, can actually be visible as an extremely bright star in the night sky. One of the most recent, except for one I'll tell you about a little bit later, it was seen in 1604 by many people, but recorded in this image by Johannes Kepler, who, in this interesting star map showing constellations, etc., had indicated the presence of this new star. And we know that this is now a supernova because in this region of the sky, modern astronomers with telescopes have been able to observe the remnant of this supernova clearly, the death of this star. Galileo is a face that most people recognize as a famous astronomer. Didn't probably invent the telescope, but was certainly one of the first people to use the telescope for astronomical observations in a serious way. And it's critical to point out that as soon as he brought this new instrument to bear in this field that had been around for more than 10,000 years, clearly, it seemed like overnight new discoveries were made. For the first time, he showed that there were satellites orbiting another planet, our own planet Jupiter, moons, much like our own. What I'll be arguing tonight is that we are on the brink of several such new eras in astronomy, and there are many more discoveries to come. I want to take a little bit more of a detour through history to kind of help paint the picture of some of the stuff later on. Astronomy changed around 1800, perhaps without even people necessarily noticing or knowing that it had at that moment. In 1800, the first evidence of light existing beyond what the eye could see, beyond the visible, was discovered by William Herschel. And in this experiment you could imagine now doing, perhaps even in elementary school. Sunlight was refracted through a prism, dispersed into a rainbow of colors. He was trying to measure the temperature of each one of these colors using thermometers, compared to each other, but also to the background in the room. What he found was that even as he pulled the thermometer past the last band of light and red, the temperature of the thermometer was still different than what it was elsewhere in the room. This indicated that there was something there beyond what the eye could see. Within a year, similarly, people had found light that came before violet in the known spectrum of light. And throughout the 1800s, our understanding of light changed dramatically. So in work leading up throughout this century and even before, up to 1865, James Clerk Maxwell published his theory of electromagnetism, where he described everything that we knew about electric forces and magnetic forces that had been understood through charged objects and magnets that existed in nature and that people had been experimenting with for hundreds, if not hundreds of years at least. Everything that was known about these things were captured in this theory that he published in 1865. In this theory, things known as electric fields and magnetic fields permeated all of space. They were created and influenced by charges and magnets. And what he discovered was that changing electric fields and changing magnetic fields could generate other changing electric fields and changing magnetic fields. and that it was possible to set up a self-sustaining oscillation of these electric and magnetic fields that traveled through the universe as a wave. We could probably spend forever talking just about this graph if you wanted to go in detail, but that's not really the point. His theory predicted precisely what the speed that this wave should travel is, and the speed was predicted in terms of some fundamental constants that had been found in the lab, ultimately, through experiments by measuring the forces between magnets and the forces between charges. And when these constants came together to predict this speed, it turned out to be exactly the then known speed of light. It had long been suspected that light was associated with electromagnetic phenomena, but this sort of sealed the deal. Why this is maybe profound to think about and reflect on in terms of the history of astronomy is there's nothing in this depiction that says the electromagnetic has to be limited to this narrow range of what we see with our eyes, and maybe just a little bit further. In fact, it could span orders and orders of magnitudes of different wavelengths, the distance between these peaks. And indeed, what we now know, of course, is the electromagnetic spectrum in the universe spans orders and orders of magnitude, and that these are all ways in which we can view the electromagnetic universe much the way we do with other astronomy. The telescope evolved a lot from its early days around the time of Galileo, becoming increasingly complex. And as you might imagine, the pace of this development was accelerated in the 20th century, like so many technologies were. Now, modern telescopes that still look at optical light your eye can see, are nearly unrecognizable. They're sort of big, robotic, behemoth things controlled by computers. There's no lens to look through with your eye anymore. Instead, it all goes to some digital camera and to some computer and on the internet. You don't even have to be at one of these places to run it. You can sit in the comfort of your own home in the middle of the night and type into your laptop. The 20th century also saw the ability to do a lot more with electromagnetic astronomy, but outside of the visible. We built instruments that could view the universe through radio waves, ultraviolet, and gamma rays and microwaves. And in many cases, the best way to view the universe actually through these wavelengths had to be by going to space, something clearly we could only do somewhat recently in history. Had we stopped here, just with the electromagnetic universe, and even just with what our eyes could see, this picture of the cosmos would still be beautiful. We'd still know that galaxies like our own seem to be as numerous as the stars in the sky. And honestly, most of what we think about when we think about astronomy really would be just told by this picture. Even for me, and I ostensibly do this as a living, this is kind of what I still think about. But in reality, what we know is that this picture is really only a part of the universe. And most of what makes up the universe is certainly things that we can't see with our eyes, and not even necessarily things that are electromagnetic. There's a lot missing here. What we've been able to do in the last few decades are open up two entirely new windows on the universe that don't rely on conventional astronomy, but nevertheless let us probe the dark aspects of the universe in pretty remarkable detail. And it's only getting better. We're really at the very first stages, just like Galileo. Okay, so to figure out, to talk about how these new windows came about, we need tiny little bit more history, I guess. At the turn of the 20th century was also a really important time for physics. We learned a lot about how the universe works on really big scales and really small scales. The first window that I'll talk about tonight has to do with physics kind of on really big scales. Einstein introduced a new theory of gravity known as general relativity in 1915. Little Freudian slip. And in this theory of gravity, the idea was that mass warped space. And this warped space would then cause some other objects nearby to change their trajectory. The interaction between the warped space and other objects in the vicinity of these warped things was what we perceive as gravity. Almost immediately after, other scientists began working with Einstein's new theory, and one of the first solutions to the equations that Einstein put forward as gravity was presented. And we now know that this solution corresponds to something that's had a tremendous impact on physics and modern astronomy, and that's the black hole. I'm just going to play a couple of roles tonight. A black hole is a place where space has managed to become so curved and so dense that there's a surface around it where even light itself can't escape under the force of gravity. And this is a great image of a black hole from the movie Interstellar. Because why not? It's a good one. You can see light actually being bent from this glowing ring of stuff. But there's clearly an outline of some region that's supposed to be reminiscent of the surface from which light can't escape, and this is called the event horizon. If you think of the event horizon as kind of a characteristic size for a black hole, even though in reality it's something we don't even know. But this event horizon has a radius of about 3 kilometers per solar mass. So what that means is if we were to take our sun, snap a finger, and turn it into a black hole, the diameter of it would be 6 kilometers, which is, I don't know, probably roughly like the size of Waterloo or something. It's an extremely dense object. Within the next year, Einstein had come up with another prediction from his theory of general relativity. And this is the theory that's opened the first window that I'm going to talk about tonight. Gravitational waves. Gravitational waves are in some sense maybe an easy thing to understand if you're willing to buy into stuff curves space. What if you have two stuffs and they're orbiting around each other? Each one's curving space, but so is the other one, and they keep moving. So the curvature of space is dynamic. This dynamic curvature of space in certain circumstances can actually ripple across the universe and be observable by people here on Earth. And even if this is kind of too esoteric about how you might generate these sorts of things, the observational consequences of gravitational waves is actually reasonably straightforward to explain. Okay, so let's imagine that binary system, is a million light years away in that direction and kind of pointing straight at us. Gravitational waves are coming through this screen. The consequence of these gravitational waves is that they are going to stretch and squeeze space in orthogonal directions perpendicular to the direction of the gravitational wave, which is coming right out of the screen. To measure this effect, in principle, is extremely straightforward. All I really need is an ambitious student with a ruler to come up here and say, yep, and just write down all those measurements. We characterize the gravitational wave by how the distance between these points is changing relative to the nominal distance between those points. We call this the gravitational wave strain. I mean, why didn't we do this a long time ago? Come on, this is easy. It's a great question. We could go into the whole history of the experimental aspect of this. I'll tell you a little bit about it. But the main reason why this has been so challenging is even the most optimistic sources of gravitational waves, where you take two of the densest things known, black holes, put them right beside each other, and spin them up at almost the speed of light. That's pretty extreme. Even if you do that, the expected gravitational wave strain that you would view here on Earth corresponds to a change in distance of 1 part in 10 to the 21. That's 1 with 21 zeros. I have no idea what that number means. I do this for a living. I have no idea. The best I can come up with, what I really mean here is it's just unimaginably small, right? Like there's no scale on which you can compare that. My favorite, people have their own favorites. My favorite is this. That's about the ratio of my height, or your height for that matter, to the entire diameter of the Milky Way galaxy. You can see why this has been a problem. So how we do this, people tried a lot of different things. This is the one that worked, so you don't hear the rest of it. How we do this is we take a laser interferometer. A laser interferometer sends a laser to a beam splitter, which splits the beam down 2 orthogonal arms. That light bounces off mirrors at each end. If the light travels exactly the same distance in both cases, when it recombines, all of the light comes back to the laser and none of the light comes here. Great. Now, if a gravitational wave or something else passes down through, it's going to stretch one arm while it squeezes the other. In doing so, a little bit of the light's going to make its way to here. By putting a photodetector here and measuring this light as a function of time, we can infer precisely how the space was strained by the passing gravitational wave. You can build a laser interferometer on a tabletop if you're not me. And when you do that, you will not detect gravitational waves, unfortunately. To be able to have the resolution needed to detect these, we had to build laser interferometers at truly massive scales. So here we have 2 detectors, laser interferometers in the US. This one's in Washington State. This one's in Louisiana. We partner with another one in Italy called Virgo. The interferometers in the US have arms that reach 4 kilometers long. In high vacuum, like the vacuum of space, and with a fraction of a megawatt of laser power circulating in them. So they're much bigger than your tabletop. These were actually built starting in the late 1990s. And in fact, we took data for 10 years, for an entire decade, from 2000 to 2010. And during that time, made absolutely no detections of gravitational waves. Yeah, I know, right? That's exactly how I felt. Nailed it. And then we had the Dark Ages. Well, no, so we're lucky as a society, I think, because certainly the people doing it didn't give up. But you all didn't give up either, and the people footing the bill didn't give up. And we had another chance. So LIGO sort of got a renovation, like down to the studs. Is this something you say in Canada? Down to the studs? Yeah, I thought sometimes these colloquialisms can be tricky, but down to the studs. Okay, so that's what you got to picture. So LIGO went down to the studs. We kind of left the frame and gutted everything else, with the promise that what we put back would produce a detector that was roughly, ultimately, 10 times more sensitive than the previous one. So after this period of Dark Ages, where people like me just sat and moped, Advanced LIGO started in 2015, my Freudian slip, 100 years after general relativity. Essentially, I mean, honestly, like literally, this is kind of true. The day we turned on, discovery happened. We detected for the first time gravitational waves here on Earth. We were able to measure directly this strain by carefully measuring this distance of 2 black holes, each about 30 times the mass of our sun, orbiting one another about 1 billion light years away. This is a sort of slow motion video. The whole thing lasted only about 200 milliseconds in terms of our data. Gravitational waves are being given off this whole time. Gravitational waves carry energy away from the system, and these 2 black holes get closer and closer together. And it's a runaway reaction, because as they get closer together, even more gravitational waves are given off. And the result of this is, after the black holes have given off all the gravitational waves, they collide together, form a single black hole, and the gravitational wave emission shuts off. We get one 200 millisecond glimpse into this available in our data. Now, I'd love to tell you that that's what we saw. It's a simulation, I'm sorry. But what I can convince you of is, hopefully, after the next couple of slides, is it's an extremely accurate simulation. And in fact, a completely realistic depiction of what could have been going on based on the data that we were able to collect. All right, so I apologize for this. This is a technical slide, which on a Wednesday night, even I don't want to look at. But I want to illustrate an important point. These new windows on the universe are just fundamentally different than what we've seen before, right? Like, we don't get to point our telescope and see these beautiful nebulae and these wonderful stars and all these sorts of things. That'd be great, but that's not what we're doing. Our insight into the universe here comes in ways that are kind of different. All we're doing when we detect gravitational waves is measuring changes in distance. We can represent this as a time series that captures how much the distance has changed as a function of time. This is the data for the first gravitational wave signal along the top row. One from the Washington State LIGO detector, the other from the Louisiana LIGO detector. I hope it's clear, even from this, without any other additional explanation or understanding, how remarkably similar those two signals are. These detectors are 3,000 kilometers apart. The chance of just randomly getting something like that to line up just at the right moment is essentially zero. On top of that, this particular signal is not just a random shape. In fact, if you look kind of at a slightly cleaned up version of this, you see that the signal is increasing in amplitude, the oscillations are getting bigger, and also in frequency, they're getting closer and closer together. That's precisely what you predict from Einstein's theory of relativity. Einstein's general relativity allows us to make very careful predictions about the gravitational wave signal if we know this is the parameters of the system. If I tell you it's 230 solar mass black holes, I tell you it's a billion light years away, I tell you what galaxy it's in, etc., I can tell exactly what gravitational wave will show up at LIGO. So to figure out what's in our data, we kind of invert the process. We propose several different models, several different masses for possible black hole binaries. We consider whether or not the black holes are spinning about their own axis like the Earth. And we fit this to our data until we get the right match. All of the physics of that binary system that we just saw is encoded in this single time series. And it sounds just like a quick blip. But we can actually tell to pretty remarkable accuracy what it is that we saw. Since this initial discovery in 2015, we've detected 10 total binary black holes. And in many ways, they're kind of all similar, but they are different. We've been able to distinguish that they're definitely different masses. Some of them are a little bit less than 10 solar masses, some of them around 40 solar masses. They cover this large range. We're starting to build a census, but what is important to point out here is that this 10 is soon going to be 100, and that 100 will in not too much longer be 1,000. And if we get our way with being able to invest even more in gravitational wave detectors going forward, we may eventually be able to, even possibly within our lifetimes, build gravitational wave detectors that could potentially see all of the merging black holes of this type in the universe. Okay. We'll come back to this in a bit, but I want to talk about the second window that we've uncovered in the last few decades. We also learned a lot about the universe on very small scales at the turn of the 20th century. And when I say this, I mean atomic scales and even subatomic scales. I'm obviously not going to talk about everything that we learned then, but there's one important thing that's going to play a really big role in this second window, and that's the discovery of the neutrino. People had begun to realize in many ways that atoms were not these immutable objects. You know, just because an atom was a certain place in the periodic table doesn't mean it had to stay there. There are lots of ways that that can change, but one of the ways that that can change is through a process called electron capture, which is quite literally if an electron kind of appears to be absorbed into the nucleus. I should step back. I take for granted that many of us have seen the models of the atom. I think we all get this cartoon, right? Like everyone's seen this cartoon. Yeah, it's a cartoon, but it's good. So we've got protons in blue, I think. Neutrons, hopefully I don't screw this up. Neutrons in gray, and electrons in kind of yellow. If we let one of the electrons go into the nucleus, we can convert one of these protons to a neutron, and give off this newly predicted particle, this ghostly particle called a neutrino. This neutrino has almost no mass and travels at almost the speed of light. But it turns out to show up in a lot of different types of nuclear reactions. It has a way of telling us about things deep, deep, deep inside complicated matter systems. It has a way of getting out of things in our universe unlike anything else could, unlike light could, because it just passes right through everything. This is the second window to talk about tonight. And the reason we're able to detect these neutrinos and learn about our universe this way is because this process can also happen in reverse. This is one of the ways that we can detect neutrinos. A neutrino could come in, it could hit, for example, a neutron, and convert to a proton, giving it also an extra electron. You might have, I probably always get this number wrong, but I think you have like billions or tens of billions of neutrinos passing through your thumbnail at any given moment. Like, there are a lot of them. That's a scientific answer. They don't do anything as far as I know. I mean, like, my thumb's fine. They don't really interact. That's the problem with the neutrinos. They just pass through everything quite easily. So if you want to be able to detect a neutrino, you have to make a big target. You have to give plenty of opportunities for at least one of those neutrinos to run into something. This is not the experiment that first detected neutrinos. That actually was 10 years before this, in 1959. And the reason I'm not focusing on that is because that was actually detecting neutrinos from a man-made source. It was detecting neutrinos coming from a nuclear reactor. The experiment was set up like 10 meters from it. I feel like that's cheating. This experiment was the first to detect neutrinos that came not from the Earth. Truly extraterrestrial neutrinos. Now, these particular neutrinos came from the sun. And the idea with the Homestake experiment was to build a giant tank, 100,000 gallons, I think, and fill it full of dry cleaning fluid. Right, I know, right? So I think it's the same stuff if you have like a spiffy wool blazer, and you get some stuff on it, and you take it there, and then they clean it for you. I don't know, I'm not fancy, I don't have any spiffy wool blazers, but I'm told that that's how dry cleaning fluid works. And this was used for reasons that I'm not even sure I understand, but the point is it has in the molecule chlorine atoms, and the idea was that the neutrino would come in and it would hit one of the protons hit one of the neutrons rather in the chlorine atom, converting it to a proton and turning it into a radioactive isotope of argon. This argon could kind of be bubbled up out of this, and you could actually count to see how much argon had been produced, to know how the neutrinos were interacting with this tank. There are other ways of detecting neutrinos. I love this picture. You have no idea what you're looking at, right? I know, but it's pretty. It's like mesmerizing nevertheless. All right, so let me help. Yes, two scientists in nice white lab coats in a rubber raft, floating inside this giant thing with these glowing gold orbs. Another way that we can detect neutrinos is not necessarily having to let them actually modify an atomic nucleus or something, but sometimes they'll just kick apart something, like an electron. They'll hit it, and they'll just smack it, and they'll knock it out of the atom. And when that electron goes flying away, it leaves a wake of light. So scientists, and this light is incredibly dim and difficult to detect, but scientists, being ambitious and clever people, tried. This experiment, the Super-Kamiokande Detector, is a detector that instead of filling it full of dry cleaning fluid, it's just being filled with water, but it can detect these neutrinos if they smack into, for example, electrons, and emit these light because of these tens of thousands of photomultiplier tubes that can detect the faintest of light that are surrounding this chamber. You can't keep this game going for too long because, at some point you just can't get the money to keep building bigger tanks. National Science Foundation and so forth are like, no, I'm sorry, you cannot build a bigger tank. But we can use the Earth, or at least things in the Earth, to also detect neutrinos. Here's an example of a modern neutrino detector that's going to play a big role a little later in tonight's lecture, known as the Icecube Detector. Here they've gone to the South Pole with this crystal clear, pristine ice. Not quite water, but pretty close. Water in frozen form, at least. So they've taken this a cubic kilometer of ice, and they've drilled holes in it and taken these photomultiplier tubes like you saw on the last slide and strung them down through the ice. This huge array of photomultiplier tubes. Now if a neutrino comes in and makes some of this faint light by kicking an electron, then you can see this light from this electron and ultimately from the neutrino flying through this ice and capture it in all of these photoelectrotubes. And in fact, you're even able to get a sense in many cases of the direction from where the neutrino came. That's why it's astronomy. This is a little bit of a digression, but an important one because it again plays a little bit of a role tonight. Similar to what we talked about in terms of how neutrinos provide this new way of extracting information about our universe through a completely different channel. It's not electromagnetic, but it lets us learn about various nuclear reactions and other things going on in objects in our universe. Similar things have led to a prediction very early on in 1933 that it's possible that you might actually construct a star-like object by perhaps maybe through gravitational collapse of normal matter that would make this electron capture process increasingly probable. What we'd end up with potentially is this ball of almost entirely neutrons. This was predicted in 1933. It's called a neutron star. And it was discovered through a couple of different mechanisms in the mid-60s. Like the black hole, this neutron star plays a critical role in modern astronomy and astrophysics. It's kind of ubiquitous. It's a source of, it's sort of a known source of many astronomical transient phenomena, and it's thought to be the end product of many supernova. Okay. Having all of these new windows, 3 total, we have our old standard electromagnetic observations, which have been around now for, since the dawn of time. We have gravitational waves and we have neutrinos, and those are 2 new windows that have just been opened in the last few decades. The goal is not to just look through each one of these windows separately. The goal is rather to be able to see the universe through all 3 of these windows together. It's a little bit like, early films, you had the silent black and white film, right? But now you've got the 3D surround sound, full color extravaganza. We want to be able to see all of that information at once. And this is a brand new field known as multi-messenger astronomy. Sorry. There have been exactly 3 examples of this so far in human history, so it's pretty new. They've all happened in the last 30 years. It's no surprise that the 2 most recent ones have happened, that 2 have happened quite recently and near together in 2017. And the reason it's no surprise is because, again, we have this accelerating pace of technology. We are building better and better scientific instruments to view the universe. We are investing in pure research and basic science, coming up with more models. We're developing cleverer and cleverer ways of analyzing the data, designing huge computer systems that can sift through all of this data in an automated way. This is just the tip of the iceberg for this field. The very first multi-messenger event was a supernova. Supernova in 1987A. This event was a first for a couple of reasons. It's actually the first nearby supernova in a long time. The first one that was close enough and in a position that you could see since 1604. The last one we talked about a while ago. So this was a long time coming. And this gave astronomers an opportunity to study it in great detail with modern instruments. And it became visible by the naked eye in the southern hemisphere, but even now it's something we can view throughout the electromagnetic spectrum. This is a composite image of radio, optical, and X-ray of the aftermath of the supernova. But even more remarkable about this first, not only was it something that people had kind of been waiting for a long time, it came along with neutrinos. This was the first time neutrinos had been associated with a transient astronomical phenomena, in this case even an extragalactic phenomena. And several neutrino detectors across the world detected it. The one that detected the neutrinos the most, and probably in some sense the most reliably, was the precursor to that beautiful Super-Kamiokande experiment I showed you with the boat. This is another boat here. This is the precursor in the Kamioka Observatory. They detected exactly 12 neutrinos. Doesn't sound like a lot, but it's more than what the background rate of neutrinos was expected to be. And in fact, because other observatories around the same time observed also a flux of neutrinos, it was really smoking gun evidence of this association. In fact, it happened, they didn't even know it happened. The neutrinos actually arrived several hours before the optical supernova was visible. It was just sort of sitting there in their data. The next multi-messenger source that I want to talk about tonight is not necessarily the next chronologically, though it almost is, but it is topically. Another electromagnetic and neutrino source. This time not a supernova, but something called a blazar. Blazars are thought to be supermassive black holes at the center of the galaxy, or center of a galaxy. They're constantly emitting sort of high energy radiation, but occasionally some of them undergo this sort of period of really intense radiation called a flare. In September of 2017, not that long ago, a blazar called TXS 0506 plus 056, a very memorable name, was in a flare state as detected by one of these space-based gamma ray telescopes that we were fortunate to build and send to space. In that same month, the Icecube detector, the neutrino detector, detected a very high energy neutrino. And this neutrino, as it worked its way through the detector, lighting up all of these photomultiplier tubes that had been drilled and buried in the ice, it gave away its position. We could tell where it was coming from. Turns out it was coming from exactly the location of the sky where that blazar was. There's a lot to this story, and it's still unfolding in many ways. If confirmed, it'll be by far the furthest known neutrino source and really a remarkable discovery. The last multi-messenger source to talk about this evening is my favorite. This is a gravitational wave source, not of two black holes, but of two neutron stars. The basic dynamics are the same until the very end. Given that these are now accessible matter, not just black holes, when they smash together, you've taken basically two giant atomic nuclei, and smashed them together. There's a light show, an incredible light show, both immediately and that lasts, well, I don't know how long it'll last because it's still going on. Another one of these graphs, because you have to learn that this modern astronomy is just not as pretty looking. But I want to show you what we saw in that moment in August of 2017. We detected a gravitational wave signal. Here, rather than showing you that time series, because of the nature of this neutron star, it's a little trickier to see that way. You can see it instead in this time frequency map. Time is still on the x-axis. Now, the y-axis is frequency, and what that's tracking is how closely spaced those cycles on the signal were. So the bigger on that axis, the higher on that axis you get, the more closely these things are spaced together. The intensity, the color rather, is the intensity, the amplitude of this gravitational wave. And you can see, hopefully, this track moving upward in both frequency and intensity as the color is brightening as you go forward. At this point, the two neutron stars have smashed together. Within 2 seconds, two independent gamma ray telescopes in space detected a burst of gamma rays. This confirmed a hypothesis for these types of events, these gamma ray bursts, that had been around for decades. In that moment, we knew this is in fact how some of these gamma ray bursts were generated when two neutron stars smashed together, because we were able to watch them smash together through gravitational waves. Within about 11 hours, after we got a little bit better of a location of this thing on the sky, a lot of reasons why things didn't go quite as we had hoped with that. But about 11 hours later, the first optical counterpart to this system was discovered in a nearby galaxy by several teams independently within really a matter of minutes. And it's a little tricky to see maybe, but each one of these tells the same story. It doesn't look like much, but you have to realize that little bright dot is being compared to an entire galaxy, right? Like this little bright dot from this exploding star is being compared to this entire galaxy full of stars. So it was this immensely bright object. And so not only was it tremendous to just get this optical counterpart, but now once we knew precisely where it was coming from, all of a sudden, all of the astronomical instruments that could be available could point exactly there and look. And what we found is that this event emitted electromagnetic radiation across the entire spectrum. Essentially, every instrument that was pointed at it saw it, all the way from radio through to gamma rays. Knowing where this source came from has led us to some other things. So you're probably wondering, well, this is all great, so what have we learned? Okay, I'll tell you a couple of things we've learned. People have known the universe is expanding for a long time. Recently, people have been able to do very precise measurements of how the universe is expanding. My understanding at the moment is there's a little bit of disagreement between the different people who have tried to make this measurement. Everyone thinks they really got the right answer, but unfortunately the two answers that people are getting disagree a little bit. Multi-messenger astronomy is a way that we can get at things, for example, like the expansion of the universe. And with this particular event, the reason why we're able to do that is the following. What the expansion of the universe means practically is things that are kind of already far apart, we're just going to keep getting further apart. So for example, the Earth and the galaxy where this is, for the most part, is getting further and further apart. The effect of this expansion of space means that light that's leaving this galaxy is getting stretched. And since it's getting stretched, it's changing its color. The wavelength, the distance between the peaks of the light is getting longer and longer, and we call this process redshifting. We can also, we can measure the redshift to things like this galaxy. And in fact, the redshift of this galaxy was known because people know certain light sources in galaxies that should have a certain color, and they can see how that color has changed, and therefore figure out what the redshift to what this galaxy is. What we can't measure accurately, it turns out, is distances. There are no rulers that really stretch that far. If we could figure out distances and redshifts accurately, then we can pin down this expansion rate of the universe. Remember how I said general relativity gives us a tool to make predictions about the gravitational wave signal that you observe here on Earth if you know the parameters of the thing you're looking for. Since we knew where this was coming from, precisely, we knew its sky position, and we knew the redshift. That, plus what we infer about the mass from the gravitational waves themselves, allow us to pinpoint the distance to reasonable accuracy. Now all of a sudden we have both the sort of ruler distance and the redshift, which allowed us to calculate, at least in a reasonable attempt at this expansion. Now it turns out, I've built up all this excitement, it's right in the middle. And that's true, but the other part of that story is our uncertainty on that number is very big. So we're not really as precise as what these other experiments have been able to do, so we're not really resolving any tensions. But this is just the first one, right? We have what I hope is a bright future of similar things going forward. And this, hopefully, we'll be able to resolve some of this tension if we haven't figured it out first. Maybe people will figure it out anyway, and that's fine too. Okay, fine, you're still like, oh, but why do I care? Okay, let me see if I can give you one more attempt. All right. I think most of you probably have a direct connection to multi-messenger astronomy right now and you don't even know it. It has long been a question about where the heavy elements in Earth come from. And among those heavy elements, a lot of heavy elements, but among them, gold. Many of you are wearing jewelry of some type, gold, platinum, other things like this. Where did that come from? Why is it here? People think, and this is still a completely viable theory, that actually it was generated in supernova. The stars exploded. This provided enough energy to cause various nuclear fusion reactions that were able to generate these heavy elements. But the merger of the Neutron Star binary in August of 2017 and the subsequent follow-up of electromagnetic observation allowed us to infer that all of the ingredients were there for heavy element production. And in fact, it is quite possible that binary neutron stars like the one that we observe could easily explain all of the heavy elements. All of the gold on all of your persons right now could have very easily been generated by some neutron star merger in our galaxy billions of years ago. Okay. Multi-messenger astronomy has had many successes, but it's still in its infancy. There have only been 3 examples. We've detected together the same source through 2 windows. The window that we've had for so long, the electromagnetic window, the thing that astronomy is rooted in, and also neutrinos. And we have an example of electromagnetic emission and gravitational waves. And I bet you can all guess what it is that we're really hoping for, but have not yet found. Really, the story is some of the things that we've already talked about could have actually been sources of all 3. Unfortunately, each one of these things is very difficult to measure. So you take difficult times another difficult, and it's very, very difficult. But we are really only in the beginning. And I think, the day will come where one of these pays off, and we see the universe, at least some part of the universe, at least one of these things, through all 3 windows at the same time. Certainly, many of us are trying, and I think we'll see it within our lifetime, hopefully even much sooner than, when I retire. But if you ask someone like me who does this, what it is that keeps us up at night, it's not just detecting yet another one of these things we already know, but rather it's detecting the things that we don't know. That's all I have. Thank you.
So the microphone is there if you have questions, and while you're thinking of your question, I'll go to the online questions. Some came in. Oh, and there were a few good ones. Where do we want to start? Let's start with you. When you started your career in physics, did you expect LIGO would work? That it would actually detect a gravitational wave? And how did you feel when it happened?
Wow. That's an excellent question. Well, I would say it depended on what day of the week you asked me. I oscillated between immense optimism and extreme pessimism, I would say, throughout my entire career. I don't think I was alone in that. I generally had a pretty optimistic attitude towards the whole thing. I certainly knew that no matter what, it was important, and that one had to try. How did I feel? Well, I don't know. It was... I felt literally everything. Like if you think of emotions as the electromagnetic spectrum, all of them in equal quantity.
Very good. Let's go in the theater.
I've got a question about, where we're going with all these detections. What are the next steps? Is it just making bigger machines, bigger buckets, as you said?
It's a good question. What I can say is, it sounds like when you put it that way, it's like, oh, gee, well, okay. I know that wasn't your intention. There's an important thing, though, which, really keeps us striving towards this progression of increasing, our technological abilities to do this. Because every time we've done it, we've discovered something that we just did not know was there. People have been looking at the sky for 10,000 years. Someone built a really crappy telescope and looked at the sky and saw something that no one thought was there. And every time we've done that, that's how it's gone. And so I think that should drive us.
All right, let's do another online question. Instead of a black hole binary, could there be a black hole trio or quartet? How many can be locked into this dance? Pretty artistic question.
That's a great question. Yeah, it turns out yeah, definitely. It gets really, the dynamics of these things become really complicated and hard to predict, even if there's more than two. But there's nothing stopping it from happening. And in fact, there are certain models for black holes, even kind of the ones that we could be detecting, where to get these black holes together, you actually need multiple black holes all kind of working in unison to sort of force these things into this close binary orbit. So it's not out of the question that even things that we've seen so far could have been the result of interactions of multiple black holes.
Thank you. Let's go in the theater.
My question is, excuse me.
That's okay. You're loud, good.
My question has to do with the updates of Virgo and LIGO. Are they going to help, and how much? And my other question is LISA, the European Space Agency program, going to contribute anything in your estimation?
Both excellent questions. Let me give a little context. So I didn't go into it, but it's in my backup slide. Oh, that's all right. I see, I knew you were going to ask this. Right now, we've just started again, so I didn't give this many details, but I sort of gave the big picture thing that we started Advanced LIGO and we're kind of just running. The truth is, we run for a little while, we stop, we make things better. We run for a little while, we stop, we make things better. And we've actually taken a whole year off. We just started up again a couple of days ago. And depending on how you estimate it, we should have a rate that's at least 2, maybe 3 times higher than what we had before. So we're headed in the right direction. Probably, it will absolutely be realized. We're going to detect more binary black holes and hopefully more neutron stars within the coming year because of these upgrades. People have done tremendous work, and the instruments are in the best shape that they've ever been in history. In terms of LISA, I think it's how some people say it, the European Space, okay. So this is a mission that takes gravitational wave astronomy to space because, that's been successful for other fields, certainly. The idea is, and I'm not up to date on the most recent LISA designs, so some of my stuff might be a little bit out of date, but the idea is to take one of these laser interferometers and fly it in space. And at least the original design would have satellites to make the arms of this interferometer. I think that we're 5 million kilometers apart from one another, orbiting behind the Earth, kind of in the same general orbit as Earth, but behind by about 30 degrees. And I think they maybe changed things a little bit, but the basic idea is the same. Now, that is going to pay off big. What it doesn't do is give us exactly the same sources that we detect with LIGO. What LISA can tell us about is much bigger black holes, supermassive black holes like at the center of galaxies that are merging. And it can also detect binary systems that are further apart and at lower frequency so that they're basically just emitting low-level gravitational waves in our own galaxy that are not yet LIGO sources.
I have one other question. Do you think the Horizon telescope program is going to contribute anything to your theory?
I am going to just stay quiet about that. There are people here that can tell you stuff if they want. There's an announcement coming up about black holes, and I don't know anything. It's not like I get special information. I'm not in the collaboration, but I guess
very timely question.
Watch the news. Sorry, I'm going to watch the news. I don't know. I'll find out when all of you do. In the theater.
You said that a neutrino can pass through anything, so does that mean it can escape a black hole or no?
No.
No? Okay.
Good question.
And then is there time for a second question?
Absolutely.
Okay. Is there anything that could cause a false detection with the gravitational wave things?
So many things. But before you get worried, we go to great lengths and have done over decades and decades and decades quantifying very rigorously, statistically, what is true and what is false. And of course, it's always a statistical statement, it's always probability. But we know with tremendous certainty that these are real. And we hold ourselves to an extremely high standard, especially for the initial detections. I could talk at length more about with you, but absolutely in the sense that it's easy to mimic a 10 to the minus 21 change in distance. Earthquakes move the ground at 15 orders of magnitude more than that. Like the Earth is a really noisy place. But that's what's made this so challenging, is years and years and years of very careful experimental design and understanding the noise sources.
Thank you. Let's keep taking questions from the theater.
Terrific lecture, thank you.
You're welcome.
Could there be, even conceptually, a fourth or a fifth window?
Oh, that's an excellent question. Wow, I was wondering if I could, I was hoping I wouldn't get that. Because like, I mean, I just can't answer that one. I mean, like if I say sure, and maybe I'm a fool because it'll never happen, and then if I say no, and then it happens, I'm still a fool, and so I just don't know. I guess I kind of hope so.
One more question.
Well, all great minds think alike, because that was going to be my question.
Ah, good.
Do you know if there's any preliminary research fields out to new ways to analyze astronomy, though, which could potentially open up a fourth hole or window?
I mean, in many ways, this is all about how you count windows. And I've been a little fast and loose with my definitions, though I think that they're reasonably well recognized in the field. For example, I mean, you might even argue that putting the entire electromagnetic spectrum into one bucket is a little unfair, right? I was joking with someone earlier in the cafeteria, like if electromagnetic astronomy is still amazing. And if it's a window, it's like the picture window, right? Like it's the big window. And you might fairly say that it itself is already some sort of different windows. But there are other ways. Okay, so there actually are other ways already, and they kind of get classified as astroparticle physics. There are other particles that can reach us other than neutrinos. The problem with a lot of particles other than neutrinos, take for example particles you know and love, protons, neutrons, things like this. We know that they're getting to us. Cosmic rays, they get to us. The problem with it is why it's difficult to put them in the same category as other things in astronomy is precisely that thing we talked about knowing where it comes from. Charged particles get all bent and distorted as they travel through magnetic fields. And unless they have an extremely, extremely, extremely high energy, they don't tell us where they come from. But maybe.
Thank you.
Ladies and gentlemen, Dr. Chad Hanna.